Okay, so thanks for joining. We'll be presenting the visibility graph and how to analyze time series as graphs. So this is a graph conference, so I guess you all are already familiar with graphs, but you might or might not be familiar with time series. That's why I will give you an introduction of what time series are and some of the techniques we have to analyze them. So first, what's a time series? Basically, it's a set of measurements that represent physical phenomenon or a phenomenon in general, and it's represented graphically as a sequence of data points over a time interval. And this representation allows us to see different measures associated with a particular point in time. So as you can see in this plot we have in the screen right now, this is the price of Bitcoin to US dollars for the last month. So each of these values you see here in the screen represents the price of Bitcoin for a particular moment in time. So yeah, here I have another example, and this is an electrocardiogram, and this is a physical representation of the electrical activity of the heart. And in time series, as this is a sequence of points, these represent successive measurements. So the time order of these values is important. So we have to keep the order of these measurements. So for time series, we have different techniques to analyze them. So some of them are quite traditional and some are really widely known. So for example, we have the mean or standard deviation, which are like basic statistics we can get from the time series. For example, the mean is the average value for the time series over a period of time. The variance, for example, is the dispersion of the time series around the mean. Standard deviation, which represents the variability of the time series. And also for time series, we have a lot of examples and a lot of applications. So we have time series for multiple domains. For example, in economics, we have time series for GDP, unemployment rates. In finance, we have stock prices, currency exchange rates. In medicine, we have the patient vitals, hospital occupancy. Environmental science, we have many more. In retail, we have sales, inventory forecasting. So many domains using time series. So they are basically everywhere. And for these traditional techniques, I mean, these ones I mentioned, they allows us to give to have the big picture of the time series. So for example, you can imagine a retail trying to get the average monthly sales for a given product or for a given store. But sometimes we have more complex systems that might require more complex methods as well, or more sophisticated techniques to do the analysis and maybe extract deeper insights. For those kind of scenarios, we have different methods. So we have nonlinear analysis as well. These techniques allows us to analyze more complex systems and try to, in order to get the underlying dynamics of these phenomena, as well as the behavior of the system. These are more expensive computationally, usually, and but they allows us to get deeper insights on what's actually going on. We have different examples. We can do fractal analysis, wavelets, entropy measurements, also analyze the frequency of the time series, and these kind of give us different measurements from the event. However, the only disadvantage I see from these methods, besides the computationally they are computationally expensive, is that the interpretability of these methods is not as straightforward as the average of a time series. We sometimes have to have some background in order to understand what does this mean, like the predictability of a time series or the complexity of a time series, if it has fractal components. I mean, that requires some information about the phenomenon itself and also about the method in order to understand what happens. However, this one allows us to get deeper insights of the phenomenon, as well as understand if there's like any unusual behavior, if there are patterns happening inside the time series, or discover some hidden structures in the data. And they have like multiple applications as well. So most of the time series I mentioned before, there are some nonlinear techniques applied on them to try to discover some information from the time series. So at this point, you might be wondering what all these has to be with graphs, or how is it related with graphs? So here is when this method comes out, which is the visibility graph technique. Oh, sorry. The visibility graph algorithm is a method proposed by Lucas Lacasa in 2008, so not so far ago. And it's a method that allows us to go from a time series to a complex network. And this allows us to analyze the time series as if it was a graph. And you might be wondering, I mean, why are we going to do that if we can analyze the time series directly? But there are some interesting results proving that some of the properties of the time series are translated to the graph. So we can implement some analysis techniques on the network topology in order to extract features from the time series. So there are results proving that random time series lead to completely random graphs, periodic time series result in periodic graphs, and time series coming from complex system with like fractal properties result in scale-free networks. So that's really interesting, and that's why this method turned out to be so popular. So in order to convert from a time series to a graph, we have to follow some steps. So the first one will be that every point in the time series is going to be mapped into a node in the graph. So I will show you an example right after, but I want to just highlight what the method looks like. And then we are going to decide on whether an edge has to be created between each pair of nodes based on something called the visibility criteria, which is this mathematical expression in the screen. But I think it's easier if I show you with an example. What does that mean? So we have this randomly generated time series, and is really simple one, and I also added colors to make it more transparent. So first, we are going to do this, what I mentioned before. So imagine each of these points is a node in the graph. Basically, we're going to try to draw a line, like a straight line, between the top of each of these bars, and that if it's possible to draw it without having any other line in the middle or any other object in the middle, that means that there's the visibility condition is fulfilled, so we can draw an edge between these two nodes. So for the first one, we can try to draw it to the second one. So I mean, of course, there's nothing in the middle. So for this one, we have visibility, right? So we can draw it, and there's nothing else in the middle. So yeah, this one stays. So we can try now for the first one and the third one. So we try, I mean, the second value is here, but it's not tall enough to block us. So we can try. So yeah, this one is clear. So this one stays. So now let's try from the first one to the fourth one. But as you can see, obviously 3 is here. So there's no way we can draw a straight line without like intercepting any other value in the middle. So we can try, but of course, this is not going to stay. And then we continue the same way for each pair of nodes. So for number 1, we try with number 4, number 1 to 5 with 6 and 7, and then so on. We go from 2 to 3 and so on. So we try every single pair of nodes, and we end up with something like this. So this is the resulting visibility graph from the time series, and I can show you how it looks like. So yeah, we went from this random time series to this random graph, and this result, as I mentioned before, if the time series is random, the graph is random as well. So these properties are the ones that add value to this method, because there are some interesting analysis you can do on time series that are or that are more complex, that lead to complex networks, and this allows us to get some insight from it. So now I will explain you a little bit of the data set I use for my use case, because I use the visibility graph to analyze a particular data set and try to extract some information from it. So I will give you some overview of it. So as I mentioned before, this is the electrocardiogram. So it's basically a representation of the electrical activity of the heart. As you can see here, this one has many components. And these components are basically representing electrical and mechanical events in the heart dynamics. One of these points is the R peak, the one we have on the top. And there's something called the RR interval, which is a representation or which indicates what's the time that elapsed between heartbeat and heartbeat. So I can show you how we can go from a time series, which is the electrocardiogram, and we can start measuring sequentially the RR interval. So between each heartbeat, we can measure how much time are we elapsing between each event. And we can create something called a tachogram, or the RR interval time series, which is the one you can see below in this image. So this first point here, the one below, represents the interval between T0 and T1, and RR2 represents the interval between T1 and T2, and so on. So we go from one time series to another. And these RR time series are really insightful, and they are used in order to determine some health conditions. One of the most important metrics we get from these time series is the heart rate variability. And that means that how much does these values change between, themselves in a period of time. So the heart dynamics is a really complex system, because as you can imagine, the heart dynamics is impacted by many factors, either external or physiological. So physical activity, hormonal activity, environmental conditions, illness conditions, if the person is asleep or awake. So there are many factors impacting in these phenomena. So that's why these RR time series are considered a complex system. And after many studies on these time series, they have discovered that there's some fractal properties on these type of series. So that's why they are widely studied. And also, as part of the data set, I have to explain that what's the chronic heart failure, which is a disease that affects the heart, and it basically enlarges the tissue, and this reduces the capacity of the heart, so it makes more difficult to propagate blood around the body. So it's a disease that affects the heart drastically, and it's affecting also the heart rate variability. So for the time series I use an open source database called PhysiNet. So for this one, I downloaded 52 time series from healthy subjects, and also 38 time series for CHF or chronic heart failure patients. I subsample this series to take only 2,048 records during the sleep periods, because these persons were measured with something called a Holter monitor, which is an electrocardiogram that is small enough to fit in your pocket, so you can have it monitoring yourself 24 hours, and you can extract the results at the end. So these devices are quite useful for this type of analysis. So the time series were super large, so I had to take a small extract in order to perform these analysis. And also, just as a highlight here, what I mean by healthy in this scenario, I mean that these persons reported or didn't report any kind of illness or condition that might affect the heart rate. Not that these persons are completely healthy, because I mean that's kind of ambiguous. So yeah, that's what healthy means in this scenario. So what once I had the time series, so I mentioned before, as I mentioned before, I had like 2048 records for each of the individuals, and that was in order to have an uniform size for the time series as well as the network, because if I have like 2048 records, I will have the same number of nodes at the end. So once I had the time series loaded in my computer, I used Python to process those series and apply the visibility graph algorithm. And once I had the visibility graph itself as a list of edges, I used Python again to upload those networks to Neo4j. And once I had them in Neo4j, I used Python again to apply some cipher queries on those networks and get the results. And I use Python just for the automation, but I mean, I could have used Neo4j itself for the analysis. But since they were like many time series, I needed to automate the process. So Python was doing the job just good. So yeah, I had Python at the end, just gathering the results back and doing some plots and analysis at the end. So this is how the time series look like. The first one is for the healthy person, and the second one is for the CHF patient. Visually, they look a little bit different, but I mean, there's not much to say about those ones at the first sight. So that's why we have to do some analysis. As I mentioned before, these are complex systems, so it's not easy to understand what's going on. I mean, the mean and standard deviation of these will give us almost nothing, right? So this is how the visibility graph look for each of these time series I showed before. So this is the one for the healthy person. This is the visibility graph. We have each node represented in the network, and the color of the node is the betweenness centrality. So that means how central this node is for the network, and the size of the node represents the degree of the node. And this is for the healthy, and this is the one for the CHF patients. So topologically, they look a little bit different. All of them are complex networks. All of them represent a time series, and also they behave as a complex network. That means that they have the small world property. They have the scale freeness. So, and they are clusters, and they form communities. So they behave really peculiarly. So this is a little bit of the code I have. I created a get metric function, which was just a function I was using to call the driver session from Neo4j, and I create many functions like this just to pass cipher queries to my Neo4j instance I had running in Docker. So I was just pulling and getting data from it. So I will show you some of the plots I got from the analysis. So this is the node degree. So here I plotted the distribution of the degree for all the nodes, for all the graphs. The blue one is for the healthy, and the orange one is for the CHF patients. So as you can see, this one is pretty similar. They follow a power law distribution, so they are complex networks. I did some more analysis because this one was not showing that much information, to be honest. So for example, this one is interesting. So I measured the average path length for all of these networks. So for healthy, you can see that the values are more around 5. And for the CHF, they're kind of 4.5, something like that. And I run a statistical analysis on this data, and it proved that these populations were significantly different one from each other. So average path length will be a good metric to try to differentiate types of time series between themselves on this graph domain. And something that was even more interesting was sortativity. So I measure a sortativity which means that well-connected nodes in the graph will tend to connect to well-connected nodes, and that means that assortativity is positive. And otherwise, when it's negative, that means that well-connected nodes will try to connect with not so well-connected nodes. And as you can see here, for healthy, the values tend to be positive, and for CHF, it stands kind of in the middle, but more towards the negative side. And I ran also a statistical analysis on this, and it turned out to be statistically different between each other. Another analysis that has been widely used in science using the visibility graph as input is this one, which is the KM plots. This is something I would say has a hybrid method, because it uses both the time series and the graph in order to do an analysis. So as you might remember from what I mentioned before, the time series, in the time series, each value of the time series, it's converted into a node in the graph. So here we use the magnitude of the value in the time series as is plotted in the x-axis, and then we use the node degree for that same value in the graph domain, and we plot it in the y-axis. And once we plot every single value in the time series and every single node in the graph, we do our linear regression on this. And it has been proven that the slope of the line that results from that linear regression gives a lot of information on the complexity of the phenomenon. So actually, I contributed in an article we published this year where we were able to use this method to discriminate between different populations, like healthy, ill persons with CHF, persons who perform regular physical activity versus persons who are not so active, and also young versus elder people. So this method also has been used a lot in detecting seismic activity in time series. There are some researchers doing that, and it has been proven to be a really, really useful method. So the visibility graph in general is a widely used method to analyze time series, and it has been used in many domains, including like financial time series, protein transcription time series, radioactivity time series, and as I mentioned before, seismic activity time series, and of course physiological. These are some of the references I used. The first one is the classic article, the one where the visibility graph was proposed. The second one, which is the one with the QR at the end, is the one I mentioned, the one I published with the research group. And this is when we use the KM plots to try to differentiate between different populations. And the other ones are kind of cool applications. The last one, I know this one in the earthquake sequence. This is from a researcher, last name Teleska. He's giving great insights from seismic activity time series using the visibility graph. And yeah, thanks for watching. Thanks for joining the live session, and also thanks for those watching on YouTube. And these are my socials in case you have any question after watching this video.